Hello everybody. I think I wanted, before doing anything, I wanted to tell you again the story of this picture. Okay, okay. So you take a ball or a sphere, and it's black, and then you drill a hole into it by, pushing the drill in, but you push the drill in a curvy way, so it's kind of knotted. Of course, the word knotted is informal here, because it's still just a tube, okay? But you don't go all the way down. You go nearly all the way down. And then you cup the bottom with a purple cup, and you connect the middle of the cup to the south pole of the sphere with a red line. And now what we have is a sphere. So the sphere is black, union a green tube, union a purple cup. I mean, just the two-dimensional surface you see here is a sphere, right? I mean, it's just this surface. It's just, it's just a sphere. Topologically, it's just a sphere, union a cylinder, and the cylinder is cupped. That looks like sort of a test tube or something. Not a test tube. What do you call the thing where you in labs where you a beaker? I don't know. Anyway, so that's a sphere, and in this sphere there is this sphere bounds a ball. This one, and in this ball there is an interval. And the funny thing about this interval is that it is knotted. Even though it looks like a tiny straight line, it's actually knotted as an interval in a ball. Because, if you were to present it as an ordinary sphere, namely if you were to pull back all the green stuff to the top, the red line will get pulled with you and will be knotted. Okay? Good, so that's just an aside, and now I wanted to talk about today's material. So, first of all, so we are, hopefully we'll finish the theorem about the composition into primes today. And the next piece of material is I want to talk a little bit about braids, and not invariants of braids, but variants of braids. So things that look like braids but are not quite braids. Okay? And I wanted to raise a question. Should we do a homework discussion class either now or either next class or at the very end, where we would just go over the homeworks and see if there are fun things to discuss? So, I don't know, would you raise your hand if you think the answer is yes? 1, 2. Would you raise your hand if the answer is no? 1, 2. So it's roughly halfway. I don't know what to say. I'll decide. I may decide to have it. And finally, homework 9 is online. And finally, let's go back to the remaining thing that we had for the decomposition into primes. So I am asserting, or we have asserted, and it's time to prove, that if P plus Q is K1 plus K2, where P is prime, then either P divides K1, and then Q is K2 plus whatever the remainder was, or the other way around, with K1 and K2 swapped with each other. Now, okay, so if we are to prove it, then let's try to prove it. So the proof, so first of all, some notation, let gamma be the curve, so it's in red like here. Okay? So this is the curve of the knot. Let B, so let but the letters were supposed to be in blue. Sorry, because black is reserved for something else. I don't know if it really matters, but I don't know. I'm wasting your time. Let's bluify this. Good. But so now B, let B be a ball separating P from Q, and let S be the boundary of that ball. So really it's S that separates P from Q. So right, it's the sphere that separates P from Q. So really what I mean is that P is in the inside of the ball and Q in the complement of the ball. And finally, let sigma be a sphere separating K1 and K2. So the inside and outside are K1 and K2. I don't know which one is which. Okay? And a priori, before you start, S and sigma may intersect in a crazy way. Okay, they come from completely different places, right? I mean, they come from different assumptions. We don't know that how they're placed relative to each other. However, let me argue that if S, namely the boundary of the ball, so if S and sigma are disjoint, the theorem is essentially proven. Theorem is proven. So why? So let's draw it. Okay. So here is gamma schematically. Of course, it's noted. Sigma is a sphere that intersects it twice. Okay? Of course, there can be notedness inside. S is a sphere that also intersects it twice. Now, without loss of generality, or we don't lose anything by assuming that sigma and S are actually tangent to each other. This is, if we start when they are disjoint, I may as well, so just push a little tube, a little finger out of S along gamma, even if gamma is noted, it doesn't matter, you can still do it. You can push it until it's here, so they're really tangent to each other. Or rather, instead of making them disjoint, they're nearly disjoint. Okay? Or maybe there is a tiny gap between them, so they are actually disjoint. Okay? And then what I know is that P is inside S, Q is outside of S, and K1 and K2, oh, by the way, I made it as if the sphere, as if the ball is inside sigma, but that's just, it would be either inside or outside, but then I could choose the point of infinity so that this picture would be right. Okay, so that there's no loss of generality in this picture. And then finally, I know that K1 is inside sigma. So again, this is sigma and this is S. So K1 is inside sigma and K2 is outside sigma, or the other way around, and I have no control which way it would be, because I lost control the moment I decided once I put infinity so that S will be inside sigma, I no longer have control, I cannot move infinity again. So anyway, that's the picture. But if you look at this picture, then, well, first of all, okay, there are actually several spheres here. There is the sphere S, there is the sphere sigma, but I can make a third sphere by tracing along sigma and then along S. Well, this is a third sphere. Okay? So, so now what do I have here? The surface sigma sorry, if this is the configuration in which K1 is inside and K2 is outside, then the surface S subdivides K1 into P and something else, right? The moment you have a sphere, it divides a sphere that intersects your knot twice. It divides it into inside and outside, and then so S divides K1 into P and something else. That something else is what you would call L, and the sphere which sphere? Oh, actually I guess what I want to say is that right, I want to show that L, right, and sigma thought of as a sphere inside the complement of S subdivides L into K2, sorry, subdivides L into, subdivides Q into K2 plus L. Okay? So, okay, sorry, I mean, so again, maybe I shouldn't have even drawn the purple sphere. Maybe I'll remove it. So, S subdivides, well, S subdivides, when thought of inside the whole plane, it subdivides, inside the whole of R3, it subdivides our knot into P and Q. But if you think of it as just sitting inside the inside of sigma, it subdivides K1 into P and L. And if you think of sigma as sitting in the complement of S, it subdivides, of B, sorry, it subdivides Q into L and K2. And that's what we wanted. So that's easy. But the problem is that generally speaking, generally, sigma and S are not going to be disjoint. So what I want to do is to, so otherwise, you know, I don't know if this is an international thing or only a Hebrew thing. So in Hebrew, zebras wear a pajama. Right? The striping, the stripes that zebras have are a pajama. Okay? So otherwise, sigma wears a pajama. Namely, here is a drawing of sigma. Well, actually, sigma is just the plane. Sigma is a sphere. And if I were to draw, you know what, let me draw it, okay? So here is sigma. Okay? Sigma has two dots, or that's the surface of the zebra. It has two dots on it. May as well put them at the North Pole and the South Pole. This is where gamma crosses. So really gamma goes through. But I don't know how it goes through. I'm not planning to draw it. But then parts of sigma are inside B and parts of sigma are outside B. And B really stands for black. So you color sigma by, so sigma is somehow divided into domains where it goes, where it dips into B. Okay, so sigma is kind of colored black and white along the intersection of sigma and S. Okay, so sorry, maybe I took too many words for that. So color sigma black where it is inside B and white otherwise. And then the boundaries between the two are simply sigma intersects the boundary of the ball B, so it's sigma intersects S, and without loss of generality or using differential geometry by putting things in general position, sigma intersect S is a finite collection of smooth closed curves on sigma. Now I want to simplify sigma intersect S, or I want to simplify this picture. The hope is to undress the zebra. So to turn its pajama either fully black or fully white, and then we're back to and then we're in the previous picture. It means that sigma is either inside the ball or outside of the ball, and that's the previous picture. Right? So we want to get rid of the complexity. So let's do it piece by piece. So if there's a black island on sigma. Now remember, sigma also has two red dots, so I want this black island to be without a red dot. So in other words, from the perspective of sigma, we have a black island. There may be some further intersection lines elsewhere. I'm not saying that there aren't. And there are two red dots, but the two red dots are somewhere else, are not inside the black dot. Okay? So what does this picture look like from the perspective of B? So now I want to draw it how as B would see it. So B, well, B sees itself as a ball. Okay? And sigma invades it at some point, but it invades it in a cup, in a disk. Okay? Because, well, that was my assumption. This is, right, on sigma, you have a black disk. Now, sigma may invade B in other places as well. So it may go through here, maybe through other places, and it may also, in fact, invade it again inside, here. Yes?
So, are the boundaries closed curves or they could be non-closed curves?
Sorry?
Are the boundaries of the intersection?
No, they're always closed. The intersection of two surfaces without boundary is a surface with is an interval with, is a one-dimensional manifold without boundary. Now, inside inside the balls are also the 2 points, and they are away from this invasion. And there is some note here, but I actually don't care. Now, there are two purple spheres. So one purple sphere is, so you see, there is a disk here. It bounds a circle on the bound on S, right? This circle, I don't know, maybe I should call it C for one of the components of the intersection. So this circle around it is also a circle on the boundary of S. So it bounds a second disk, so it bounds one disk on sigma and another big disk on S. And if you glue two disks along their boundaries, you get a ball. Sorry, you get a sphere. And the inside of a sphere is a ball. So you get one purple ball here. And I actually don't care about it. And the second purple ball here. So basically, the complementary one. No, I do care about that one too. Okay? So, do I care? No, I don't, in fact. Sorry. So I got a new purple ball. Maybe I will call it, oh, P is already the name of the knot, so let me call it V for violet. Yes?
The first purple ball you drew, should it cut the green line?
Yeah, it does. It cuts the green line. But I don't care about it. The point I was going to make, the point I'm going to make is that V, so replace, so the way you deal with this situation is you replace B by V. And now the knot is inside a ball that intersects sigma in fewer places. Because we've gotten rid of the original of the intersections of C, of the curve that led us to think about it, and maybe we've gotten rid of even more, and we haven't added anything new, because the only change we made was we went along sigma, and sigma doesn't self-intersect, so there are no other intersections that get created.
Sorry, could you explain two things? First, where is the curve C in the second picture? Like what?
Oh, the curve C in the second
second
picture looks like 2 points, these 2 points. Because really really it's a curve that looks like this. Okay, so, I've drawn sigma as a line, but sigma is a surface. It's a surface that has a hat, a cap, I don't know what to call it, that goes into the ball B. Right? So,
yeah.
Okay?
Yeah, okay, I see it now.
Good. Okay, so that's first case. Second case, so if there's a white disk on sigma without red in it. So, in other words, if in sigma you have a white disk somewhere, so the black is outside, and of course there could be more intersection lines, and the 2 red dots are not inside this white, so I don't know, they're somewhere else. Okay? So again, what does this picture look like from the perspective of B? So from the now I'll draw B as a disk, right? So this is B, and I'm drawing it as a disk, but you should be thinking that it's really a ball. And sigma somehow peeks out of it somewhere, looks outside somewhere, and of course it may look outside somewhere else, and it may even, it maybe do something crazy, but it peeks out at some place. And here where it peeks out, so if I'll call this disk here, inside here, I don't know what to call it, D, then this is D here. D is this green disk. Okay? So nothing else crosses through this green disk. Okay? And the resolution, and I should say that the knot is somewhere else. Okay? So here there may be some knot P. So the resolution is exactly the same, but the other way around. So you take this disk and if you glue it to this disk, you're gluing two disks along their boundary. Their boundary is this curve C here, which is again like here. So if you're gluing 2 disks along the boundary, you get a ball. The inside of this ball still contains P, and you've removed the intersect, so purple would go just a bit outside, so maybe I've misdrawn purple, I don't know if I can delete it without making a mess. Oh, I could. So draw purple to go just a bit outside, parallel to green, but just outside. So you've gotten rid at least of the original intersection. Okay? Good. Next possibility. Okay, so if there are no well, if there are no black disks or white disks without a red dot inside, then the picture, so maybe I'll pause and say what the picture must look like. So the picture must look like, so we have our two dots, and they are separated by concentric rings of black and white. So in the plane there is simply nothing else that I can write. I mean, anything else would contain either a white disk or a black disk. Okay? So the next case is I actually want to get rid of this case. So the case where you have a black region with a dot inside it. So next case, a black disk with a red dot inside. So again, this looks like, oops, sorry, I ran out of paper. Okay, so this looks like, on sigma, so what sigma sees is a black dot, a black disk, well, just what I said, a black disk with a dot inside and another dot somewhere else and possibly other lines. Okay? What S sees, sorry, not S, B, what the ball sees is, here is the ball. There is a knot inside it. This is knotted. I'm not pretending it isn't. And green pushes in somewhere, and it pushes in a way that so that the green disk cuts through the line of the knot. Okay? And it may push in other places. It may push in here again, and it may push in, no, it cannot push in from the side because these we've already eliminated. But it could push in like this, I don't know, it could be, it could do other things. Okay? Now, however, this green line, nothing cuts through it, other than the knot, other than the curve gamma, nothing cuts through this piece of green line, because because that was our assumption that this is a solid black disk. Okay. So now I can divide the disk B into two disks, namely V1 and V2. So really I'm dividing it using this disk. Okay? Now, since P is prime, P, so P, well, okay, I've divided this disk into two pieces, in this ball into two ball shapes, separated by a sphere. So, so P lies either in V1 or in, I forgot to give a name, to V2. So P lies in V1 or V2. So simply take the new ball to be wherever P lies. So if P is in V1, replace, actually let's say VI. If P is in VI, where I is 1 or 2, replace B by VI. Okay? So in either case, you reduce the number of intersections because you've gotten rid at least of the intersections that we started from. And you don't create any new ones. Okay? And you're still enclosing P. Okay. And then the last case is the hardest. So I actually don't have anything useful to say about the case if there is a white. So if you have a white disk with a dot inside, I don't know what to say. Okay? You draw the picture and there is nothing that comes to mind. Okay? But I do have something to say about if there is a black ring. So, I mean, if you have such a thing and not everything is white, then there will be a black ring somewhere with the red dot inside it and the other red dot outside it. So you may have several such black rings, sorry. So there may be another one here. And maybe more. Okay? So let's draw it now from the perspective of B. So this is how sigma sees B, and now let's look at how B sees sigma. So, so B is again a ball. Then the curve gamma passes through it. Now, each loop in sigma that surrounds the dot, that surrounds one dot, that separates the two dots, has linking number 1 with the knot. Actually loops around the knot. So it also has linking number 1 with the with the knot. So it also surrounds the curve. So it also goes around from the perspective of B. So these intersection lines, I don't know, C1, C2, C3, C4, are also intersection lines that go around from the perspective of B. Okay? So from the perspective of B, so now so from the perspective of B, the picture must look like this. So you have so what I've drawn now is a black annulus, right? A black ring, like these black rings that we did before. So, right, because so I've drawn a cross section, and you should be thinking that this is so this goes all the way around, okay, or more, okay, so here is the black annulus on the green sphere, okay, but I'll just draw it as a pair of opposite arcs. Now it could be that there are more, so I will not draw the rest, but I'll only say that there could be more green arcs. So there could be, I don't know, another black annulus here, and another black annulus here, and they could be nested, so there could be another one here, okay? But whatever it is, I want you to take an innermost one. So if there are plenty of black annuli, take an innermost one. So in other words, take take an outermost one, I'm sorry. So take a black annulus, well, I do want to draw it bigger. So take a black annulus such that in these, so there are disks on this, on B, on S, there are disks on the sphere that are bound by this black annulus, and I want these disks to be empty. Sorry, these are not disks, sorry. This is an annulus on the sphere. So if you look at this edge and this edge, and remember that you rotate it, so there is an annulus also on the sphere, and I want this annulus to have no further intersection points. So maybe I'll give names to these annuli. So this will be A, so A is also this, and the annulus on the black sphere will be A prime. So this is also A prime. Now there can be further intersection points, like further annuli, like here, or another one like that, I don't care. Now do something funny. So, not funny, I don't know, do something. So, down at the bottom there is a disk. There is a disk that goes from here to here. So, thicken it a little bit. I don't know which color to use. Oh, blue, I suppose. So thicken it a little bit. And now it looks like kind of a bent coin down at the bottom. Or more precisely, it's a disk multiplied by an interval, topologically. Okay? And now, and now there are two balls in this picture. So one ball is, well, let me draw it. So it's this one. Okay, so what is this ball? So it's obtained by gluing A to A prime. So you're gluing two annulus together, so you get a torus, right? If you glue two annuli to each other along their boundaries, you get a torus. So you get a torus from these two lobes, and then you connect, and then you add a disk, this coin that I've added at the bottom, and it shuts down the annulus, it seals the whole of the annulus, so you have a sphere. So the thing I've drawn here in purple is a sphere, so it has an inside, and this inside is a ball. And let's call this ball V1. But it also has an outside, and in fact I can describe the outside also by drawing purple curves. So it has an outside, and the outside is also a ball. Call it V2. Now, one of V1 and V2, or V2, so one of the VI contains P. Basically because P is prime, so V1 and V2 subdivide the ball into two, one of them must contain P. The reason I have shown the picture at the start, so the reason I've shown, where is it? Oh, it was far long ago. The reason I have shown this picture is to emphasize that we don't know whether it's the top or the bottom that has P. So, you see, I know that this disk is a standard disk. I also know that that V1 being bound by a sphere is a ball. But I don't know that if you restrict your attention, maybe I'll draw it to the, maybe I'll draw it again. So I don't know that if you look at the shape M, that is, so so let M be the torus, the thing, the inside of the torus whose cross section is shown here. I don't know that M is a standard torus. Okay, I know that it's well, I mean, if you have a torus in R3, it subdivides the space into two subspaces, but I don't know, into two subsets, but I don't know that M is a standard torus. I do know that once I append to it this coin, it will become a standard ball. But before doing it, it could be a non-standard torus. So if it's a non-standard torus, it could be that P is actually inside it. So P could be inside V1 or inside V2. I don't know which one it will be. But whatever it is, replace B by that VI, and you have fewer intersections. Okay? And we're down one intersection. Or in fact, well, we're down one zebra stripe. So, I mean, well, you know, we're out of time, but it's probably an excellent idea to go through the proof, assuming that the green surface is the surface shown here. So the picture that I have here, you know what, forgive me, I'll go a second more, so I'll copy paste this to the bottom, and so let me just paste it here. Where's the mouse? Oh, here. So it's probably a good idea to go through the proof thinking that sigma is, well, some ball that extends what I've shown here. So in that case, and the curve gamma runs through the middle of. So in this case, you get a zebra stripe on sigma. It's shown here where, and the two annuli, so A and A prime, so A will be the cylinder, the tube that surrounds the knot between these 2 points. The A prime will be just the shell of the ball minus 2 discs. If you insert the extra disc, so the extra disc that I've inserted at the bottom is right here, then it becomes standard, but before that it isn't. And here the knotedness is in, so P is in V1. So V1 is the outside and V2 is the inside, and the knotedness is in V1 in this picture. Well, I mean, okay, it's probably not convincing because you have to go through it. Maybe I don't know how to describe topology in a convincing way. But I don't know. Let me make it a semi smiley for the end of the proof. So if you review it, you will find that everything is that I never told lies, but it might not be apparent. So yeah, see you on Monday. Questions, comments?
Is there a reference for this book?
So it's in Licorish's book. So you can see Licorice, Introduction to Knot Theory, and it's actually, I mean, I can tell you what page it is, pages 19 to 21. But Licorice ends the proof in a different way, which I think is too complicated. So it's nearly the same up to the very end, and then at the end he says something completely unnecessary, to the best of my understanding.
I don't know if I can ask another question.
Sure.
So the zebra stripes was kind of confusing for me. So if I should describe it in this way, so if I take kind of the surface of a water to be, let's say, the ball,
So B.
and I inflate some balloons, kind of make it a horn, and maybe let it appear above the surface. I don't know if you get what I'm trying to say.
I'm not sure I get what you're trying to say, but I don't think there is much room to be confused about the zebras, or the details might be confusing, but the zebra is basically, so you take the ball,
Yeah.
right, and the green surface comes in and out of it. I mean, I've drawn it as a two-dimensional, as a one-dimensional thing, but it's a two-dimensional thing that goes in and out. In itself, the green surface is a ball. So basically, think of this ball here as if it's made with ink. I don't know. So it colors sigma with patches of black, which could be discs or annuli. or more complicated, I mean. So, okay, sigma, well, I've actually drawn sigma here as a sphere, as an S2, but an S2 is really a plane, okay? So sigma is really a plane with infinity inserted. So on this plane, there are curves of intersections with S, and every time you go into S, you go into B, you color black. So you get a zebra pattern on sigma. Let me stop the video and again